Maximum flows and minimum cuts in the network. We now continue with the analysis of the Ford-Fulkerson algorithm, an activity that will occupy this whole section. In the process, we will not only learn a lot about the algorithm, but also find that analyzing the algorithm provides us with considerable insight into the maximum flow problem itself. Analyzing the algorithm flows and cuts. Our next goal is to show that the flow that is returned by the Ford-Fulkerson algorithm has the maximum possible value of any flow in G. To make progress toward this goal, we return to an issue that we raised in section 7.1, the way in which the structure of the flow network places upper bounds on the maximum value of an ST flow. We have already seen one upper bound, the value V of f of any ST flow f is at most C equals to the summations of CE, summing for all E out of S. Sometimes this bound is useful, but sometimes it is very weak. We now use the notion of a cut to develop a much more general means of placing upper bounds on the maximum flow value. Consider dividing the nodes of the graph into two sets A and B so that S is in A and T is in B. As in our discussion in section 7.1, any such division places an upper bound on the maximum possible flow value, since all the flow must cross from A to B somewhere. Formally, we say that an ST cut is a partition AB of the vertex set V so that S is in A and T is in B. The capacity of a cut AB, which we will denote C of AB, is simply the sum of the capacities of all H's out of A. That is, C of AB is equals to the summations of CE, summing for all HE out of A. Cuts turn out to provide a very natural upper bounds on the values of flows as expressed by our intuition above. We make this precise via a sequence of facts. 7.6. Let F be any ST flow and AB any ST cut. Then V of f is equals to f to the out of A minus f to the in of A. This statement is actually much stronger than a simple upper bound. It says that by watching the amount of flow f sends across the cut, we can exactly measure the flow value. It is the total amount that leaves A minus the amount that swirls back into A. This makes sense intuitively, although the proof requires a little manipulation of sums. Proof. By definition, V of f is equals to f to the out of S. By assumption, we have that f in of S is equals to 0 as the source S has no entering agencies. So we can write V of f is equals to V to the out of S f to the out of S minus f to the in of S. Since every node V in A other than S is internal, we know that f to the out of V minus f to the in of V is equals to 0 for all such nodes. Thus, V of f is equals to the summations of V f to the out of V minus f to the in of V, summing for all vertices V in A. Since the only term in this sum that is non-zero is the one in which V is set to S. Let's try to rewrite the sum on the right as follows. If an HE has both ends in A, then f of E appears once in the sum with a plus and once with a minus, and hence these two terms cancel out. If E has only its tail in A, then f of E appears just once in the sum with a plus. If E has only its head in A, then f of E also appears just once in the sum with a minus. Finally, if E has neither end in A, then f of E doesn't appear in the sum at all. In view of this, we have the summations of f to the out of V minus f to the in of V, summing for all V in A is equals to the summations of f of E, summing for all E out of A, minus the summations of f of E, summing for all E into A, which is equals to f to the out of A minus f to the in of A. Putting together these two equations, we have the statement of 7.6. If A is just a subset with one singleton s. Then f to the out of a is equals to f to the out of s, and f to the in of a is equals to 0, as there are no agencies entering the source by assumption. So the statement for this set A equals to the set S is exactly the definition of the flow value V of f. Note that if AB is a cut, then the agencies into B are precisely the agencies out of A. Similarly, the agencies out of B are precisely the agencies into A. Thus, we have f to the out of A is equals to f to the in of B, and f to the in of A is equals to f to the out of B. Just by comparing the definitions for these two expressions. So we can rephrase 7.6 in the following way. 7.7. Let f be any ST flow and A be any ST cut. Then V of f is equals to f to the in of B minus f to the out of B. If we set A equals to V minus the set T and B equals to the set T in 7.7, we have V of f is equals to f to the in of B minus f to the out of B, which is equals to f to the in of T minus f to the out of T. By our assumption, the sink T has no living agencies, so we have f to the out of T is equals to 0. This says that we could have originally defined the value of a flow equally well in terms of the sink T. It is f to the in of T, the amount of flow arriving at the sink. A very useful consequence of 7.6 is the following upper bound. 7.8. Let f be any ST flow and A be any ST cut. Then V of f is less than or equals to C of AB. Proof. V of f is equals to, by definition, is f to the out of A minus f to the in of A, which definitely is less than or equals to f to the out of A, because f of to the in of A could be positive. So by definition, we rewrite it as the summations of f of E, summing for all h E out of A, which definitely is less than or equals to the summations of CE summing for OE out of A, because the flow value is usually less than or equals to the capacity value for each h. So by definition of the summations of CE, that's equals to the cut value between A and B. Here the first line is simply 7.6. We pass from the first to the second since f of f to the in of A is greater than or equals to 0. And we pass from the third to the fourth by applying the capacity conditions to each term of the sum. In a sense, 7.8 looks weaker than 7.6 since it is only an inequality rather than an equality. However, it will be extremely useful for us since its right-hand side is independent of any particular flow f. What 7.8 says is that the value of every flow is upper bounded by the capacity of every cut. In other words, if we exhibit any ST cut in G of some value C star, we know immediately by 7.8 that there cannot be an ST flow in G of value greater than C star. Conversely, if we exhibit any ST flow in G over some value V star, we know immediately by 7.8 that there cannot be an ST cut in G of value less than V star. Analyzing the algorithm, max flow equals mean cut. Let F bar denote the flow that is returned by the Ford-Fulkerson algorithm. We want to show that F bar has the maximum possible value of any flow in G, and we do this by the method discussed above. We exhibit an ST cut A star B star for which V of F bar is equals to C of A star B star. This immediately establishes that F bar has the maximum value of any flow and that A star B star has the minimum capacity of any ST cut. The Ford-Fulkerson algorithm terminates when the flow F has no ST path in the residual graph GF. This turns out to be the only property needed for proving its maximality. 7.9. If f is an ST flow such that there is no ST path in the residual graph GF, then there is an ST cut A star B star in G for which V of f is equal to C of A star B star. Consequently, f has the maximum value of any flow in G, and A star B star has the minimal capacity of any ST cut in G. Proof. The statement claims the existence of a cut satisfying a certain desirable property. Thus, we must not identify such a cut. To this end, let A star denote the set of all nodes V in G for which there is an SV path in GF. Let B star denote the set of all other nodes. B star is equal to V minus A star. First, we establish that A star B star is indeed an ST cut. It is clearly a partition of V. The source S belongs to A star since there is always a path from S to S. Moreover, T is not in A star by the assumption that there is no ST path in the residual graph. Hence, T in B star as desired. Next, suppose that E is equals to UV is an H in G for which U is in A star and V is in B star, as shown in figure 7.5. We claim that f of E is equals to CE, for if not, E would be a forward H in the residual graph GF, and since U is in A star, there is an SU path in GF. Appending E to this path, we would obtain an SV path in GF, contradicting our assumption that V is in B star. Now suppose that E prime is equals to U prime V prime is an H G for which U prime is in B star and V prime is in A star. We claim that f of E prime is equals to 0. For if not, E prime would give rise to a backward H E prime prime equals to V prime U prime in the residual graph GF, and since V prime is in A star, there is an S V prime path in GF. Appending E prime prime to this path, we would obtain an S U prime path in GF, contradicting our assumption that U prime is in B star. So all H's out of A star are completely saturated with flow, while all H's into A star are completely unused. We can now use 7.6 to reach the desired conclusion. B of f is equals to f to the out of A star minus f to the in of A star, which is equals to the summations of f of E, summing for all E out of A star, minus the summations of f E, summing of all E into A star, which is equals to the summations of CE, summing for all E out of A star, minus 0, which is equals to the cut between A star and B star. Note, now in retrospect, we can see why the two types of residual H's, forward and backward, are crucial in analyzing the two terms in the expression from 7.6. Given that the Ford-Fulkerson algorithm terminates when there is no ST in the residual graph, 7.6 immediately implies its optimality. 7.10. The flow f bar returned by the Ford-Fulkerson algorithm is a maximum flow. We also observe that our algorithm can easily be extended to compute a minimum ST cut A star B star as follows. 7.11. Given a flow f of maximum value, we can compute an ST cut of minimal capacity in big O of m time. Proof. We simply follow the construction in the proof of 7.9. We constructed the residual graph GF and performed breadth-first search or depth-first search to determine the set A star of all nodes that S can reach. We then defined B star equals to V minus A star and returned the cut A star B star. Note that there can be many minima capacity cuts in a graph G. The procedure in the proof of 7.11 is simply finding a particular one of these cuts starting from a maximum flow F bar. As a bonus, we have obtained the following striking fact through the analysis of the algorithm. 7.12. In every flow network, there is a flow F and a cut AB so that V of F is equal to C of AB. The point is that F in 7.12 must be a maximum ST flow, for if there were a flow F prime of greater value, the value of F prime would exceed the capacity of AB, and this would contradict 7.8. Similarly, it follows that AB in 7.12 is a minimum cut. No other cut can have smaller capacity, for if there were a cut A prime, B prime of a smaller capacity, it would be less than the value of F, and this again would contradict 7.8. Due to these implications, 7.12 is often called the max flow min cut theorem and is phrased as follows. 7.13. In every flow network, the maximum value of an ST flow is equal to the minimum capacity of an ST cut. Further analysis, integer value flows. Among the many corollaries emerging from our analysis of the Ford-Fulkerson algorithm, here is another extremely important one. By 7.2, we maintain an integer value flow at all times, and by 7.9, we conclude with a maximum flow. Thus, we have 7.14. If all capacities in the flow network are integers, then there is a maximum flow F for which every flow value f of E is an integer. Note that 7.14 does not claim that every maximum flow is integer valued, only that some maximum flow has this property. Curiously, although 7.14 makes no reference to the Ford-Fulkerson algorithm, our algorithmic approach here provides what is probably the easiest way to prove it. Real numbers as capacities. Finally, before moving on, we can ask how crucial our assumption of integer capacity was, ignoring 7.4, 7.5, and 7.14, which clearly needed it. But how crucial? First, we noticed that allowing capacities to be rational numbers does not make the situation any more general, since we can determine the least common multiple of all capacities and multiply them all by this value to obtain an equivalent problem with integer capacities. But what if we have real numbers as capacities? Where in the proof did we rely on the capacities being integers? In fact, we relied on it quite crucially. We used 7.2 to establish in 7.4 that the value of the flow increased by at least 1 in every step. With real numbers as capacities, we should be concerned that the value of our flow keeps increasing, but in increments that become arbitrarily smaller and smaller, and hence we have no guarantee that the number of iterations of the loop is finite, and this turns out to be an extremely real worry for the following reason. With pathological choices for the augmenting path, the Ford-Fulkerson algorithm with real valued capacities can run forever. However, one can still prove that the max flow min cut theorem 7.12 is true even if the capacities may be real numbers. Note that 7.9 assumed only that the flow F has no ST path in its residual graph GF in order to conclude that there is an ST cut of equal value. Clearly, for any flow F of maximum value, the residual graph has no ST path. Otherwise, there would be a way to increase the value of the flow. So, one can prove 7.12 in the case of real valued capacities by simply establishing that for every flow network, there exists a maximum flow. Of course, the capacities in any practical application of network flow would be integers or rational numbers. However, the problem of pathological choices for the augmenting pathways can manifest itself even with the integer capacities. It can make the Ford-Ferguson algorithm take a gigantic number of iterations. In the next section, we discuss how to select the augmenting pathways so as to avoid the potential bad behavior of the algorithm.